Because the table shows how the activity of a radioactive sample varies with time. You use the data to confirm the activity decreases exponentially. The thing about exponential decrease that's unique and it separates it from other types of decrease is that when there's exponential decrease, it decreases by the same factor over each unit of time. For example, let's say here we take 1 hour. Okay, so the factor of decrease here is 93.5 over 120, which is basically 0.78. Okay, if I take another hour, and it doesn't have to be the next one, but any another hour, the decreasing factor here is 72.8 over 93.5. Okay, so that's again, it's the same factor, and you can do it again. You can take any 1 hour period, and you should find that the activity decreased by the same factor over those periods. I don't even have to take 1 hour. I can take, for example, let's say in this case I'm taking 3 hours. Okay, the decrease there is times 0.47, and if I take another 3-hour period, you should get the same decreasing factor there. Okay, so we can confirm that this does decrease exponentially because the factor of decrease is the same. Okay, I've got the same set of data here, but this time we're trying to confirm that it's an exponential decrease, but graphically, because that means plotting a graph. So if we plot a graph of activity against time, we do get a decrease, but we can't be sure that this is an exponential decrease. It could be something else. So what we're going to do is we'll look at the equation, and we'll try to turn this into a straight line. Okay, to figure out what to plot, I'm going to look at this equation, and I'm going to compare it to y equals mx plus c because I want a straight line. The first thing to do is actually take natural logs on both sides. Okay, and then using your log rules, you can separate the terms inside the log on the right hand side. And then using again your log rules, that actually just simply becomes minus lambda t on the right there. So then I'm going to rearrange this in a way that's a bit easier to compare. So here, if I plot on my y-axis ln a, on my x-axis if I plot t, then my gradient will be minus lambda, and my y-intercept will be ln a naught. Okay, so I now want to plot ln a against t. So I'm going to make a column. I'm going to use my calculator to take the natural log of the activity, and then I can plot that on a graph like this. However, this y-axis isn't suitable because we're wasting too much of the space on the graph. So you don't have to start your y-axis value at 0. Okay, in this case, it's better to start the y-axis values around 3. Okay, if you take it at 3, we get a graph like this. So you can see using more of space there. And when you work out the gradient, it's more likely to be accurate. The fact that this is a straight line confirms the relationship that is an exponential decrease. Okay, so now we want to find the half-life and the initial activity. To get the half-life, we need to find the decay constant from the gradient of this graph. Okay, and then the initial activity, to be honest, you can just read it from the graph over here. Okay, but however, I'm going to show you how to figure out that the initial activity from the graph. So first, the gradient is equal to minus of the decay constant. So if I take a gradient, make sure you read 2 points from the line, and you very clearly write out change in y over change in x. Okay, here I'm using my time in hours, so I'm going to get my decay constant in per hours. Okay, so if I just take minus that, that is my decay constant. And then to get the half-life, I will just do ln2 divided by my decay constant there. The initial activity comes from the y-intercept, which the y-intercept is actually equal to ln of the initial activity. So to get the initial activity, you need to do e to the power of the y-intercept. Okay, so in this case, e to the power of 4.8, which is the y-intercept. And that gives me initial activity of 122. As you can see, there's a bit of error reading from the graph.